Hi, I want to tell you how I used an internal hardware timer 2, to decode the DCF77 signals. The DCF signal, it's only important that you can decode 2 seconds, 1 second, 200 milliseconds and 100 milliseconds. This is for a 0 bit or 1 bit, this is for each second, and this is for second 59. So I draw me a diagram. This is the internal high HSI clock frequency of 60 megahertz. It goes to a clock divider register. You can program. We set it to 0, so it divides by 1. So the clock is coming out is also 60 megahertz. Then we goes to the prescaler of timer 2. We set it to 10, so it divides it to a factor of 2 power 10. It's 1024, resulting in a frequency of 50,625 hertz going into the counter. And with this frequency, we have to calculate these theoretical values. But it didn't work. I got all kinds of problems. So I communicated a lot of time with ChatGPT, talking nonsense, giving sometimes good hints. I posted a message on the STM8 forum. I have spent 3 days with all kinds of experiments testing that the main cause that it didn't work is that the system clock is not 60 megahertz, but it is 14.45, about that. So it is not calibrated in the factory. Therefore, I had to change the prescaler clock divider. Let's set it to 0. This is the megahertz. But then I had to change the factor from 10 to 9. That causes all the problem. So the frequency that's coming out is 28.230 hertz. And then, now we are talking, these are the values. If the timer overflows, it's 2.3 seconds. With this value, you have the 2 second signal. This one counts is 1 second, this count is 200 milliseconds, this count is 100 milliseconds. And with this value, my DCF receiver detects the signals perfectly. Well, I would like to explain how I decode the DCF77 signals. Maybe some of you are not interested in the deeper part of it, but I am. So I want to explain to you how I use it. So if you are not interested, you can just skip this part. But first of all, I'm using a timer, a hardware timer 2, that counts to 56,535. It's a 60-bit timer. Initially, you can set an I/O port, which is connected to the pulse coming out of the DCF77 receiver. You can set it to generate an interrupt when it's going high, low, or whatever. You can, but I said it. I do not speak about high and low, because if you use an inverter, the signals are swapped. So I'm talking about active and inactive signals. First, you start to go to the configure the port pin where the data is coming in to an active going edge. So then sometimes there is an active going edge. Immediately what is done at this part, it swaps the interrupt sensitivity, as it is called, to the opposite side, to an inactive going edge. Personally, interrupt sensitivity, I think it's my first thoughts are this is some analog thing, but it's not. It's just the way the port pin reacts on interrupts. So the signal goes active, the interrupt sensitivity is set to inactive. So if it's going down, there's an interrupt generated again. Interrupts are generated on each activity. When the interrupt is activated here, the program knows which edge the sensitivity is set to, So it knows it's a going inactive signal. So it knows at this time it reads out the timer 2, and it's within 1 millisecond, 100 milliseconds, within some offset, it decides it's a 0. But if it goes down here, the timer is read out twice the value, then it knows it's a 1. Timer goes on. If in between there is some illegal signal going high, nothing is done, because the timer is only checking the times of 100 milliseconds, 200 milliseconds, 1 second and 2 seconds. If it is between, it just doesn't react. It just inverts the edge sensitivity, so it's ready to find the next active edge, which is 1 second from here to here. So this is the next bit. So both interrupt events, going active or inactive, call the same function which analyzes the interrupt edge detection and the timer timing and decides has it received a 0 bit, a 1 bit, or a 1 second bit, so it's the start of the next bit, or a 2 second bits, which means this is bit second 59, so all information is complete, and this all works perfect. I don't know if you are interested in how to set up a project from the base up. I start with creating a source folder, and in there I may set all my modules. One of the modules is the peripherals. The peripherals that are those hardware items that are inside the computer, like the beeper. But the I/O ports, you think about a microcontroller has I/O ports, or the I/O ports are occupied by some peripheral like a UART or so. But the I/O port itself is also a peripheral. So therefore, I created my own one. Port, some functions, the header files, and what you see here is the I/O port .h file. I created myself, but all things project defines. That's my own project defines. We go to it, and then you can see the most important things are to include STMS8H. This contains all register names and corresponding addresses, and this file contains the microcontroller specific implementations. We can open this first one. Is a very big file, very long file. This is a shorter file. You can go open, and this is special to the STM8S103. You can see here it's about port definitions with the corresponding addresses in memory of the microcontroller. But anyway, just include those two files and all will work fine. So now we go back to the I/O ports, my I/O ports. It's a hobby of mine. I don't know why, but I like to create my own macros or defines of all signals. Like this, port P0, P1, P2, P3 until 7. Configure it as input. I use this ASCII art to make my source coder more readable. I use a lot of this kinds of documentation. But you can see the output data register of port A. I set OR it or in exclusive OR it with some of the defines I made here. So these are the masked pin 0, 1, 2, 3. Why is there a U in type before? Otherwise the compiler gives me a warning. It will work, but the compiler gives a warning. So to avoid this, in strict ways of programming C, you have to use a U and A. Now, in this way, the three basic and input floats, set as input float, input with pull-up, input with external interrupt, disable, input external interrupt, enable, input external interrupt, disable, and so on, and so on, and so on. These, on a late night, you just can create this very easily. Just copy, paste, and do some renaming from port A to port D, B, C, D, etc., etc., etc. And then finally, you go to the end, you make a combination of all possible. You make a define of all possible combinations. So let's look at high-low. This is a get function, so read out a port. Check, this is a check function. Check high or low. Port A bit 0 to 7 to port E. Port E is not available in the STM microcontroller, but I still embedded it in my defines, but I never use them. Set them to output push-pull fast or slow. Fast, then you can output more faster signals, but it costs more energy. So if it is not needed, you set them to pull low or slow. It costs less energy, but if your microcontroller is powered up by some USB adapter or whatever, it doesn't make sense. So that's the most output pseudo open drain. That's also possible. I do not explain it here. Output high low, set the output to high low. So all combinations, but finally you can configure each pin, each output pin, by a simple check, not a check, still the configuring, but you can set any combination you can set with one single macro. That's what I use. So when initializing the whole microcontroller, there is a I/O port module, which you are looking now, and on the init, it initializes all pins with pull-up to be sure that all pins are in a stable condition. And then each port can have an interrupt handler. Here we have the interrupt handlers. Port A, B, C, and D. I only use port A. Dus if I enable the interrupt on a compare event, so when a timer has reached a certain value, or when it overflows, then this interrupt handler, this function is called automatically. And in this function, I call it an output socket, I can call a function what's in this variable, and this variable is loaded by the connect function. I call it also output socket. So from elsewhere you can call this function, hand over a pointer to a function, and when the port A interrupt handler is executed, it automatically calls that function that you filled in previously, but it first checks if it's not 0, because then there's nothing to call. Not 0, then it calls that function. So you can hand over a function to this interrupt handler, and that function will be called if an interrupt is active. So here in the module syscontrol, which is the main module that is executed, you can see I call here this function, the I/O port function, with some function, a DCF77 decoder function, remote receive DCF signal handler. Well, and in this DCF77 decoder function, no, it's not there, it's there. It's this one. This is the function that is executed each time an interrupt, a level change on port pin A1 that's connected to the DCF77 receiver is happening. And as an argument is given the edge detection. Is it an active edge or an inactive edge? So this function has to know, is an active edge or inactive edge? Is it an active edge? I have to restart the timer. It is an inactive edge to measure the width of the signal. Then it doesn't restart, but it checks if the counter value is between the expected values to report it as a 0 or a 1, or as a 1 second byte, or as a 2 second byte. I hope you understand a little bit what I'm talking about. I always also want to give you some information how I used these variables. These are the 4 distinctive variables to check: 100 milliseconds, 200 milliseconds, the 1 second and the 2 seconds, timer, counter, counts. I use the word timer, but it should be counter. But anyway, I'm used to it. I just define them. Number of timer ticks should be counter ticks for a 0 bit, for a 1 bit, for a 1 second, for a 2 second. And I give me some percentage in offset, because you must check if the timer value is between this value plus or minus a certain percentage. You can use absolute values, where I prefer percentage. So the offset for these 4 timings are the number of ticks times the percentage divided by 100. And 100 is, for me, it's define the number of cent percentage. So I can put here the value 100, but it doesn't make sense. You don't understand why is it 100. But if you say def number cent per percentage, it's defined in my other file as 100, so you understand what's going on. So this is the offset. So now you have to, for this 4 values, you have to min and the max, min max, min max, min max. So 4 min maxes for the 0 bit, for the 1 bit, for the 1 second, and for the 2 seconds. So you calculate the number of ticks for a 0 bit minus the offset and plus the offset, and then you do it for all 4 items. And well, then you use these values in your comparison. So the interrupt handler knows if it is an active going or inactive going edge. If there's an inactive going edge, this function is called evaluate inactive signal. And here you find the counter value. Is it greater or equal than the minimum value for a 0 bit? And is the value also less than maximum for a 0 bit? Also, we have the same here for a 1 bit. So it decides it's a 1, or it decides it's a 0. Well, thanks for watching this video until now. This was a little bit about software, but in my next video I will explain and try out to decode these 60 bits of data that is coming each minute received from a DCF77 receiver. But I'll see you in the next video.